Okay, so as we said before, these matrices tend to be very sparse, so we want to do something about that. And the solution is what we call word embeddings, which is much more dense and compact. And the approach, there are many approaches. We'll talk about a couple of, or we'll mention a couple of them at the end. But the one we're going to describe is the word-to-vec, and in my opinion, is probably one of the the most famous one. And it has two different models. All right, it has the scriptgram model and it has the BAL model, the continuous bag of words. The difference is that in one of them you take a word and you try to predict the context words, and the second one you do the opposite. You take the context word and you try to predict the target word. All right, so this was inspired by previous work by Yoshua Bengio, 2003, about language models. But the guy that actually did this work is Thomas Mikolov, who is now at Facebook. And let's see what this is about. All right, so the idea is pretty simple. This structure that you see here in neural models, it's called autoencoders. All right, autoencoders always have the same shape, and the shape is something like this. You have an input, and then you have a middle layer that is smaller than the input. So if this is dimension V, this one has a dimension D that is much smaller than V. And then you go back to the same size as the input. So your output here is the same size as the input. And in autoencoders, usually your input is the same thing as your output. So you try to predict the input. Maybe you can ask, like, why would we do that? There are many, many reasons why you can do that. We can discuss this in class, but for this specific application, what we are trying to do is that we're trying to find a lower dimensional representation of the input. Because of all the reasons we said before, we don't want a sparse matrix. It's more computation, it's less efficient, and also not as great as what we're going to obtain. All right, we're gonna get rid of some noise and stuff. All right, except that the word2vec is not a pure autoencoder, because as we said, we're not going to get a word here and we're going to predict the same word. Rather, we're going to take a word and we're going to predict the context words. Or the opposite, we're going to take the context words and the input and try to predict the word. So it's not like a pure autoencoder, but it's almost the same thing. Okay. All right, so in the input you have a single word in one hot representation. So here you can see everything is 0. So as you can if you have probably guessed, the number of neurons here in the input will be the size of the vocabulary. So you have the whole vocabulary here, and you have one word is 1 and the rest are zeros. All right, now in the output you're going to have a softmax activation. So as we said, what softmax does, it takes a vector like this, and you have some values here, value 1, 2, 3, and 4. You pass it through softmax. And what softmax will do for each one of these values, for example, the first one will be exponential of v1 divided by the sum over I of exponential of vi, right? And here exponential of v2 divided by the same thing. So these things will sum up to 1, and they will all be between 0 and 1. They will be positive values. So it looks like a probability distribution. So if you have a softmax activation, the outputs, and as we said, the output have to be the same size, then you're going to see what is the probability of the context words given the word that you have in the inputs, and you're going to try to maximize that. So those words that actually appeared in the context have to have a higher probability than the others. All right. So if we look at the skipgram model, where we take the word and we predict the context, you have this is the input and these guys are the output. So what you're going to do, you're going to push this in the input as a one-hot vector, and then you're going to watch for the probabilities of these words. And these probabilities should be higher than the other words that never appear with the word eat. Okay. Now your error, because these probabilities have to be high or as high as possible, or higher than words that never appear with the word eat, the error function should always be something that you want to minimize. So what you're going to do is you're going to add a minus here, and this is going to be your error function. Okay, and the error function is just a combination of all of these context words. All right, so you're going to take the error for this word and this one, and this other one, and this other one, or each one of these guys. You're going to take the probability of each one of these guys, and you're going to log doesn't really change much, except that it's, you know, it's nicer, and you can have a sum instead of a multiplication, etc. Everything that we have seen before in language models. But you're going to add this minus because you want to make it an error. Otherwise, you need to maximize instead of minimize. All right. All right, so that's about the same. And continuous back of word models is the opposite. So you're gonna do, this is your input, is the context, and the error will be the error for the word that you have chosen as a target. Okay. All right, so if you do this, you're gonna end up with something beautiful that we call analogies in the world of word embeddings. And because, you know, you can see that each word is a point and a semantic space, and you can join them by vectors, which would be basically the difference using the, you know, the origin 0, 0. You can actually do operations over words. So you can say the vector of king minus the vector of man plus the vector of woman, it's almost equal to the vector of queen. So if you do this, you're going to end up very close to queen. That is something very, very special about embeddings that we can do. And you can do much more than this. You can do, for example, relationships that, for example, France, Paris, Italy, Rome, etc., etc. How do you do this? So for example, you can say, you basically say, I have the word France and I have the word Paris. So these are words that you suggest because, you know, you have knowledge and you know that this one is the capital of the other one. And then you give the name of a country, like for example, Italy, and then you ask or you compute with your vectors, you're saying, if I use the same vector that helped me move from the point France to the point Paris, and I put it and I do the same thing to Italy, where do I end up? And you will see that you will end up very close to Rome. Same thing if you do this, same thing if you do that. You can do also when you go from an for example here, name and occupation, right? Occupation or whatever the person was known for, like for example Picasso, painter, Mozart, violinist. You can do CEO relationships, you can do food relationships, you can do all kind of analogies. They're not exact, of course they fail sometimes. There are, in the NLP world, there are competitions of analogies to see who can do analogies better. But this is something that was completely impossible to do when you had only the one hot vector to represent your words. So this is the word of word embeddings, and obviously if you are doing any kind of NLP nowadays, you have to think about where do embeddings fit in the picture. All right, so we talked about word2vec, that is Glove. That is another way of doing things. So Glove came from Stanford, specifically Richard Socher under Professor Manning. And they don't use actually neural models. It's a different story. Another thing that is very important to know is that either you can pre-train your models. That means you can take, for example, Wikipedia. And from Wikipedia, you can compute your metrics M, where you have all the words that appear in Wikipedia and their representation. And then when you have a classification problem, like let's say you're doing sentiments, then for each word in your sentence, you do a lookup in this table and you bring the embedding and then you kind of find a way to combine the embedding of each word and then you classify. But there is another way of doing things is, probably we'll see this sometime, but you have a one hot vector as an input and you add a layer called embedding. And at the beginning, you just initialize this with random numbers. And then you have your layers, and then you have your classification here at the end. When you do back propagation of the error, not only you change the parameters of all the layers, but you also change your embeddings. Okay? And so the embeddings you're going to end up with are going to be very, very specific to this classification task. Versus this one, you built it on Wikipedia or some big corpuses, so it is for more general purpose, and then you're going to use it for different things by tweaking the parameters here. These embeddings here are specifically for this classification. If you read NLP papers, this is called static embeddings, and this is dynamic. Okay, so usually when you are doing experimentation, you want to show how good is your approach using dynamic and static embeddings. Right. So this is it for this part, and for the next lecture, we're going to talk about word sense disambiguation.